Okay, so let's look at the next equation. So for the next equation, we're going to be looking at displacement, and displacement is given by area under the velocity time graph. Okay, so let's look at this shape, this area that we have under that graph, and let's split it into two shapes, into a triangle and a rectangle. And when we do that, remember the area of a rectangle is base times height. So remember our height is u and our base is t in this case. So we can calculate the area of the rectangle in that case as ut, and our triangle is a base of t and a height of 80. And when we put those together, we end up with a formula that says displacement is equal to ut, the area of the rectangle, plus half 80 squared for the area of the triangle. So in the last case, what you can simply do is you can use algebra to derive. Before we get to the algebra, we can also look at this shape as a trapezium, and the area of a trapezium there is given by the length of base 1 plus the length of base 2 times the height over 2. So we can invert this. We can invert it like this so that it looks clear to us. So you can see that the height there becomes time, and your base is u plus v divided by 2, and you multiply by the height there. So that gives us our other formula, this one here. So we now have three equations just by looking at the geometry of the velocity time graph. So the last thing that we need to do to derive the last formula, we are going to use algebra. So I'll show you how that can be done. But it's also important to note that all these formulas are as a result of the fact that our graph has constant acceleration, or this straight line here. So this straight line here is constant acceleration. If you have a different case where the acceleration is not constant, then all these equations don't work. So we said it's a precondition that your acceleration must be constant. If it ceases to be constant, then you have to break down your question or your problem into sections of constant acceleration, because the formulas do not work if acceleration keeps on changing or is not constant. So that's what's represented by this curve. If we have a curve here, we no longer have the triangle that we used to derive the one of the formulas. We no longer have our area under the graph as before. So all those displacement equations no longer work. So you need constant acceleration. So let me show you how to derive the other formula. Okay, so for the other formula, what you could simply do here is manipulate your algebra. You could simply use algebra. So if you take that formula that we got from our trapezium, and you can make t the subject of the formula, okay, and then you substitute into this formula the first formula that we started off, and when you do that, you do your algebra there, and you simplify, you end up with the last formula. Okay, so this one you can derive it from this equation and this equation, make t the subject of the formula, then substitute into this equation and simplify, and you end up with this formula. Okay, so we now have all of our equations. So what's left is that we must be able to use these equations to solve our kinematics problems or problems of motion. And remember, we should have constant acceleration when we are solving these problems. So in our next tutorials, we're just going to be throwing around some questions and using these equations. Let's try to look to do our first example here. Okay, so let's do this question that says a dog is running and starts to get faster at 2 meters per square second for 3 seconds. The dog covers 20 meters. The dog covers 20 meters over this time, what velocity did it start with? So we are looking for initial velocity in this example. We're looking for initial velocity. So the first thing, step one, is to define one direction as positive and the other one as being negative. So you can see the dog is running in one direction here, so we can just take that direction as our positive. When the dog is running forward, that's your positive. If it happens to turn around and come backwards, then that's going to be negative. Remember, this is important for your velocity and your displacement and also your acceleration, which are vectors. Okay, so with that in mind, we have the dog going forward as our positive and going backwards as negative. So we create a table like that for the SUVAT variables, and we ask ourselves, what variables are we given by the question? So we can check here and see that we are given the acceleration at 2 meters per square second. You are also given the time, and you're also given the displacement, which is 20 meters. And also, once you have 3 of these variables, you can pick an equation so that you can find the fourth one. So the fourth one here is what the question is asking us, which is your initial velocity. So we are going to look for an equation that is an S, a U, an A, and a T, and use that to make U the subject of the formula and calculate and solve for U. So you can do that. You realize that that's the equation there in purple, and you do your rearrangement there and you do your substitution. You should be able to get 3.7 meters per second. So let's end with this first example, and in the next tutorials, to those who were with me physically, we were just doing all sorts of calculations, and then we went on to talk about waves. So I'll also roll out some videos that involve that talk about waves. So I'll meet you in the next lessons, and you can always book for your online tuition so that I continue to make these videos for you and we continue to study our physics.